Good. The last part I still have, so we have 20 minutes more. So I can quickly go through the more motivational slides if you want. So we do that. Some more slides on trends in computing, let's say. So let me open up the slideshow. And then we also see if the recording would record that one. Good. And let me put this on play. So you see the slides? Everyone sees them? Okay, good. So the slides are really just a motivation basically into computational methods. So I want to quickly go through the computational trends and then show you how we would work with these heat flow and wave propagation examples and the different methods that we would basically see in this class. So in terms of trends, it's something that you have to keep reminding yourself that when I started my PhD, there was 2004. I think so, yes, 2004. And if you would check out what the fastest machine at that time was, I think there was around the time of the Earth simulator in Japan, which was the fastest machine. So the orange curve gives you basically the top machine. The blue curve, the lowest one, gives you the slowest machine of the fastest 500 machines worldwide, and the green one would be the sum of all these top 500 machines. And if you start today in 2020, so the fastest machine just came out in June. That's a machine called Fugaku in Japan, which is now the fastest supercomputer. And that one, if you look in terms of the floating point operations it can do. So here, the scale of the performance is floating point in double precision. And in double precision, it's about almost 500 petaflop per second. So 500 double precision floating point operations per second that this machine is doing. If you decrease the precision, if you go from double precision to single precision and to half precision, then actually this machine tops the exascale capacity. It is the first exascale system ever built by now. People were projecting that actually, like 5-10 years ago, that the exascale machine will start around 2020. And we are still more or less on this projection actually, on this increase, almost exponential growth increase. So you see the scale on performance, it's a logarithmic scale. So we are still like almost doubling the performance every year. People keep on shouting out that, oh, we will flatten this curve at some point, but we'll see if that's really a trend that's happening or not. But the thing you have to remind yourself is that the machine you will have now at the top in 5 years when you finish your PhDs, they are again considered to be old and overcome by even faster systems. So this computational trend, it's increasing tremendously. Yes, these #1 machines are often prestige projects, but machines like Fugaku, machines like Summit, the previous #1 machine, they are often used for science actually. So they are open for science. And so if we have challenging problems, we can get access to these biggest machines, to these biggest supercomputers. And the point is basically, don't forget that the problems we want to solve become more and more complex. And in that sense, computational methods help us to find solutions to those, and we can scale up to very large machines actually. If we actually look at the different fields, we usually see that earth science is more or less a small player compared to, for example, physics and especially material science. So chemistry and material science are usually taking up the big bulk of a machine in terms of using it. And earth science here is around 13%. So this is for the machines at the Swiss National Supercomputer Lab or Center, which had Europe's top machine for the last few years. And so earth science is always around 10 to 13% in terms of usage. It's kind of a small player when you compare it to other fields. But still we do have access to these machines often, because the topics we study often they have a relevance to society. If we study earthquakes, it's because of the risks that earthquakes impose and the damage that they can cause, that then they become relevant to society. So we do have access to these machines. So good. So it's very likely that we can have these machines. And here is basically something that I want to make you aware of, that at the moment, the speed up that we can get through applications is not by just buying the new hardware anymore, a better CPU, a better chip, which will be faster, but the way we speed up things now is by parallelizing problems. And this has started very early on, actually. So 2004, it kind of already started. By 2006, you had these multi-core CPUs. So a CPU was not only a single core CPU anymore, but they added multiple cores to it who could do computations. And then the application you were running on it was faster, not because the chip was clocked faster. So the clock speed kind of leveled out, but it was because it has now multiple cores and you could do things in parallel. And this is still by today, is basically you make an application faster by parallelizing it and run on multiple cores, and not by increasing the clock speed of the chip anymore. The reason is that the clock speed basically is linked to the energy consumption of the chip. And the more you speed it up, the more hungry it becomes, the chip. So it increases the energy usage. And that's basically a trend which had to be stopped. So before that, you basically just wrote a single process program. You didn't care about parallelizing it. And you could buy the newest hardware and it was faster because the chip was clocked faster. So it was able to do more computations. But already by 2006, that was stopping basically this trend. People often didn't realize until years later that if they want to speed up their programs, they had to parallelize them. The same here, basically, this was about a single process computation where things just slowed down, basically. That already happened when I started my PhD. So the message here is really you have to parallelize now your codes in order to be able to take advantage of the new systems. Again, this is more or less a similar trend here, a similar picture. For example, when you look at the blue dots, that would be a single process program. And the performance kind of flattened out basically by 2010. So if you're not parallelizing your program is not faster than 10 years ago. Good. So how does a chip look like? If you look like at the physical chip, that's, for example, a typical way of a layout of such a chip. So you have some shared memory, the shared L3 cache, that's shared memory between these different cores. You have then here in this case 4 different cores. So 4 cores which can do actually computations. And then you also have a chip, a graphics processor dedicated just for the graphics. And so what do you think is the most costly computation your laptop is doing or your workstation is doing? What is the biggest computation it does? So if you turn it on, you have an idea what's the biggest time-consuming computation is your laptop is doing or the workstation is doing?
Sure.
Say it again.
It's sure.
I don't understand.
It's you mean it's what consume the memory?
No, what's the floating point operations? What's the most demanding application you're running in terms of floating point operations, in terms of computations? It has to do.
I would say graphics.
That's right.
So similar video and data streaming.
So what the most demanding computation is that the laptop or your workstation is doing is bringing the colors onto the pixels of your screen.
Oh, yeah.
So each pixel on your screen has a color, and that needs to be determined, that needs to be computed. And that's the most, by far the most expensive computation your laptop is doing or your workstation is doing. And for that reason, if you see some of these cables between the monitor and the workstations, in the past they have been really thick cables they needed because there was a lot of information that needed to be transferred from your actual workstation to the monitor. So it does that like at 60 Hertz, I think, frame rates. You have, I don't know, millions of pixels on your screen. It does that computation. It has to be really fast. And that's the most demanding piece, basically, computation piece in your laptop or in your workstation, is bringing the color onto the pixels of your screen. And that's why the graphics processors became more and more powerful, actually.
And we have CUDA technology to help for that problem.
And it's something we come to, basically. So at the beginning, we couldn't really use the graphics processors. But then a few years ago, NVIDIA made it possible to have the graphics processors for general computations. So by then we could start using the GPUs for our scientific softwares. And the GPUs have been already very powerful. they have been very dedicated of being fast in doing this number crunching to determine pixel colors. But then it became actually a more general computing hardware, which we could use basically. We come to that point in a second. So you have cores, the cores do basically the computation, and then the graphic processors brings it onto the screen. And if you look by the number of cores, typically you have a chip here, it's like from 2018, it was 6 cores. You could turn on hyper-threading, so you had 12 different threads or 12 different processes at the same time that were able to run in parallel. The base frequency is this 2.9 gigahertz. The lithography is basically how small the transistors became. It's 14 nanometers. So they shrink that more and more, and then how power hungry the chip was, it was 45. So if you switch to this year, it's 8 cores, 16 threads. So the number of cores increased a bit. The base frequency is more or less the same. Lithography is still the same, but also the power consumption is still the same. What it means basically, a lot of the current design of new chips is constrained by how power hungry it can be. So it has to be power efficient, but at the same time, you want to basically increase the computational performance of the chip. So the chip becomes better in terms of handling floating point operations per second. So the number of flops increases. At the same time, the power kind of remains the same or even decreases. So they become more and more energy efficient, actually, these chips. And it's driven by this, it's driven by the mobiles. So in mobiles, in your laptops, in iPads, etc., you want to have a chip which uses as little energy as possible, so that the battery in your mobile stays up for as long as possible. So that's pretty much the motivation of developing new chips, basically, make them more energy efficient, but mostly because of these things, mostly because of mobiles, etc. So if you look at the number one machine, this Fugaku machine, the fastest supercomputer, it uses this kind of chip. It uses an ARM architecture. That's kind of new. ARM is kind of an open architecture, which vendors can start implementing. And in this case, the chip now has about 48 cores plus four cores for like background processes. And 48 cores are used actually for the computations. So in total 52 cores, but 48 for computation. And the machine is really just basically a CPU machine. So this is the CPU. It has no other computing chips, etc. Base frequency is about 2.2. You see the lithography went down to 7 nanometers. And at some point there is a physical barrier which you cannot go below it. Otherwise you start having quantum tunneling effects, etc. in these transistors. So that's going to be a barrier which people discuss and debate quite a bit. So where is the physical barrier of your lithography? How small can you become before your machine is vulnerable to quantum effects, for example? And in this case, these 48 plus 4 cores take about 160 watt, which gives you about 16 gigaflop per watt. So that's basically a measure of how many flops per watt can you do. It's a measure of how energy efficient basically it is. Good. And then became basically also to hardware accelerators. Intel had this program with Intel PHYs. So they had an additional hardware which was accelerating computations. It was really just used for computations now. They call it the Intel PHY. And then they had these chips you could either plug in into your existing hardware or as an extra chip on your motherboard, for example. So some of the supercomputers use these now as accelerators to speed up the machine, but Intel stopped this program now, basically. So they're not continuing with these separate hardware accelerators. Intel is more like going the way of increasing this, basically, the number of cores on your CPU. Now, when we come to computation, GPU became more and more powerful now because of this graphics problem. They had very early on very dedicated hardware, very dedicated chips, these GPUs, which could do number crunching to get the pixel colors. But then basically they opened it up for more computations. You had capabilities of doing floating point operations with them. And so the GPUs basically, since about 2006, 2008, these Tesla architectures became general purpose chips, which means for general purpose computations, you could use them. And they have basically the advantage of these accelerators is they are just made and designed for number crunching. They don't have all the sophistications of a CPU chip, but you make sure that if you add two numbers, that the result is the same no matter which number comes first, etc. The chip, the GPU didn't care much at the beginning about these sort of things. If a single pixel has a wrong color, it doesn't matter much. So there was not much of like making sure that the operations were done in a correct way and always giving you the same result. So they don't had that at the beginning, and now they added it more and more a bit to make it more secure. Of when you run now a computation on this GPU chip, that the result is more or less the same, no matter how often you run it. And these chips also, you see the trend of these peak performances, and the trend just increases. It also just keeps doubling, basically year by year. So at the moment, we actually are beyond Volta already. Volta is this chip here. It's a graphics processing unit, GPU. The advantage they have much more cores, basically, than the multi-core chips. So in principle, people kept separating CPU as a multi-core and GPU as a many-core chip, because the number of cores for GPUs were just way higher, basically. You see the base frequency is lower, and the base frequency often determines how power hungry your hardware is. And in this case, actually, it's quite hungry. So it's about 300 watt that this GPU needs. But it has way more cores. And if you compare them, basically how energy efficient it would be in terms of flops per watt, it's at 26 gigaflops in this. This is double precision per watt. So if you look at Fugaku, this one had 16 gigaflop. And this one has 26. So in principle, it's way more energy efficient, a GPU. But this is as a peak performance. And often when we run stuff on the GPU, we hardly use 10% of the peak performance. So in principle, the actual number of floating point operations we would have when we run a wave simulation propagation on the GPU is maybe 1/10 of that. And for CPU is a bit higher usually. So you can maybe reach up to 80% of the peak on a CPU, while on the GPU it becomes way more demanding of writing a program which actually uses the peak performance. So when we use a finite difference scheme, we need a lot of memory reads and less of multiplications and summations. So the number of floating point operations compared to the number of memory retrieves we do is quite low when we use, for example, a low order finite difference scheme. If you increase the order, then you have more multiplications per memory request. And so then you become more efficient of using these chips. But it's very tricky actually to use the peak performance of these chips, because often our schemes are bound by the memory accesses they need. So they need to read numbers out from these cache memories, for example. And that's always a bottleneck. Good. The newest chip they have, the GPU, is an Ampere A100 chip. Is that you see the power, it still increased in terms of double precision. The energy efficient actually decreased slightly. But these new chips, they are more and more made for machine learning now. So they not only have double precision cores, but they have lower precision cores. And in particular, the GPU architectures from NVIDIA, they experiment with tensor cores, which when you put it into a very particular format, it becomes very fast to compute. And this is the top 500 at the moment. So the fastest machine, the fastest 10 machines, determined in June. So you see Fugaku is the #1 machine with this almost 500 petaflop. The ones I highlighted here are the ones which use GPUs or hardware accelerators. So the second machine, Summit, uses NVIDIA GPUs, Sierra uses GPUs. Then we have Sunway, we have Tianhe 2, which uses the Intel accelerators. HPC 5 uses accelerators. Selene uses accelerators, these A100 chips, GPUs. Frontera is more or less a CPU system, but then Marconi and Pittstain, again, they use GPUs. So from these 10 fastest machines, you have, 6 machines with GPUs or hardware accelerators. And what is interesting as well is, so far these machines, they all have been government machines, the fastest machines. Fugaku, financed by Japanese government, Summit, US, Sierra, US, Sunway, Tianhe 2, China. But now HPC 5 and Selene, these are machines which belong to private companies. So HPC5 is oil and gas company Eni in Italy. Selene is NVIDIA, who is running its own computer, its own supercomputer. And this is interesting to see, actually, that you have now companies coming up with their supercomputers as well in these top 10. So when you are going to work for NVIDIA, you have access to Selene. If you're going to work for Eni in oil and gas, you have access to HPC5. So you do have these supercomputers in-house. So having expertise on running stuff on such machines actually is helpful. It's giving you an advantage, basically. It's a useful skill to have. So keep that in mind. And at KAUST, we have Shaheen 2. It's a CPU system at the moment, which is the large supercomputer. Plus then we have the IBEX cluster, which is a more heterogeneous cluster, which also has some GPU nodes in it. And KAUST is in the phase of replacing Shaheen 2 with the new machine. And they are now evaluating basically what kind of system that machine should have. Should it be CPU only? Or should it have some sort of GPU accelerators in it as well, etc. So they are evaluating the systems now. Good. So let me quickly finish up. We are way over time already. Let me quickly show you the geophysics part and the methods part that we want to do in class. So in class, basically what we will do is we start solving these 1D problems for heat flow, basically how heat dissipates. For example, if you have a rod, you start heating it in the middle. How is the temperature expanding in this hot? That's the heat flow equation. Then the wave propagation. Again, basically you would have a rod, you hit it in the middle, and then you see these waves propagating out, etc. And we solve these simple 1D problems just to see how actually the method works, basically. There's very simple problems in 1D, but then we solve it with these different methods to see a bit, compare these methods a bit, get a feeling for it. We will also have the higher order finite difference scheme. We're going to solve, for example, tsunami waves, a simple code. I think that one comes, for example, from Caltech, the template where we propagate basically tsunami waves. And then compare these different methods with each other, for example. So we have finite differences. We have pseudospectral methods, and then finite element methods that we're going to solve. The finite element method, for example, a half-space cooling problem is also something we're going to implement. So how is the plate cooling basically off from like a mid-ocean rate, etc. And then also like the wave propagation part, which we will touch, for example, with the spectral element method. This is kind of a candy, a fun simulation just recently made with the spectral element method for the moon, basically, in this case. And the source here is a meteorite impact on the moon, which happened shortly after Apollo 16 mission installed seismometers, basically. So you had the Apollo missions which went to the moon. You had Apollo 12, 13 didn't make it to the moon. You probably saw the movie about Apollo 13. They had problems arriving at the moon, so they couldn't plant. But these Apollo missions, they all put seismometers on the moon. So you have Apollo 12, 15, 16, and there's also Apollo 14 mission. And shortly after the Apollo 16 mission, there was this meteorite impact here in the middle of the picture, you see. And a way of studying now the internal structure of the moon, for example, is by looking at these seismic records that we have from the moon. And this is a meteorite impact in the 70s, I think 72 was that impact. And by basically simulating now how the seismic waves propagate out of it, we can then compare that against the actual data and trying to understand more about the internal structure. Here it's the moon. Obviously, we do it for the Earth as well, but now also for Mars. There is the InSight NASA project who is running, which put a seismometer on Mars. And so we want to actually also do seismic wave propagation on Mars. So I'll let you run this simulation. What you will hear is you hear the seismic trace basically, which would be recorded at Apollo 12 and at Apollo 16. But the range is not hearable of the seismic, of the ground shaking. The frequencies would be too low. So in order to hear them, I transpose basically the frequencies. I tune it up into an audible range. So what you hear on the left side is Apollo 12, on the right side you hear Apollo 16 station, how it would sound like. Good. So that's how it would look like. At the beginning, I wasn't sure if I was doing something wrong when I implemented this. But you have this kind of blinking pattern here. If you go at the beginning, you see how the wave field kind of disappears, reappears, disappears. Now disappearing, appearing again, disappearing, appearing again. And I wasn't sure if something is wrong the way I visualize it. But what I think now, basically, when I looked at it, is you do have reflections from the outer core. So the moon has almost similar structure in terms of there is a solid crust and upper mantle or mantle. And then there might be an inner core with a very distinct, different composition, and might be even fluid. And as soon as the waves basically hit that core interface, would be like the core mantle boundary in the Earth, it's reflecting again the seismic waves. And then it kind of interacts with the surface waves that propagate along the surface. That's why you see then this kind of flickering at the beginning, which I found very interesting when we started that. Good. So let me finish here. We are a bit over time. So basically that's the idea is just, we do a lot of it numerically. A lot of what we're doing in geophysics is now computationally oriented. And so it's good to get an idea of these different numerical methods. And that's what the class is about, basically. Do you have any questions, suggestions, or remarks whatsoever? So I can stop sharing that. Things are good? Good, then let us meet tomorrow again. And we make it now 7:30. Is that good? So an hour earlier, 7:30. Let's meet again on Zoom. And then I show you a bit how we start with the conservation laws, for example, to derive the equations that we want to solve then numerically. And then I guess then by the end of this week, you have a good idea of what this class will be about. And then you can decide if you want to continue or if you want to drop it, etc. But it gives you hopefully a good view, overview into what we want to do. Good. Is there anything else you want to say? Questions whatsoever? No?
No.
Check.
Everyone's fine? Good.
Yeah.
Shall I leave this on, this Zoom meeting, for you to talk with each other? So we ended. Shall I make a breakout room? I don't know how that works, but somehow we have options to do that. So that you can, I don't know, get to know each other.
I have another class, so thank you very much. Bye
When
bye.
is your class starting? Now? Now,
2:15.
Faustina?
Minutes ago.
Yeah.
5 minutes? Okay, good. Ask them about changing the time.
Okay, thanks. Bye.
Hopefully that works. Good, bye. So see you tomorrow, everyone.
Thank you.
Thank you. Thank you.
Thank you, Professor.
Professor.